We have passed 9:30, so I would like to begin the webinar and welcome you all to this Cheers CLC webinar, which is the third in our series. Our first was last year in July, which summarized the design basis work. 2 weeks ago, we had a webinar summarizing the feed studies for the demonstration plant. And today we will focus on one of the key features of chemical looping combustion, the oxygen carrier. And there has been an intense laboratory and pilot testing program, which my colleagues today will share with you. So we have a lot of material to cover. I'm going to cut my welcome address short here by saying that we have a Q&A option for everyone. So type in your questions as the presentations go, and our panelists will try to cover them as soon as they can. And if we have some time left in the end, we'll cover some of them orally if needed. So I give then the screen over to the work package leader, Øyvind Langøyen, who is a senior research in SINTEF.
Yes, thank you very much, Todd, and welcome everyone. Yes, we will present the work that has been done on oxygen carrier development within the Cheers project. And the speakers you see here, it's Yngve Laring from SINTEF, Kristina Bachuc from IFPEN, Inge Sonum from SINTEF, Lei Liu from Tsinghua University, and myself, Øyvind Langøyen. First, some small words of the Cheers project. Cheers is short for Chinese European Emission Reducing Solutions. It's an international R&D project to demonstrate a second generation CCS technology, also carbon capture technology, at the relevant size, taking it up to TRL 7 level. It consists of European partners, partly funded from the EU Horizon 20 program. They are Total Energies and IFPEN from France, Silesian University from Poland, and SINTEF and Bellona from Norway. The Chinese partners, they are Tsinghua University, Zhejiang University, and Dongfang Boiler Group. And they are co-funded from the Ministry of Science and Technology in China, most. So a main deliverable from this project is to design, construct and operate a chemical looping combustion demo unit of a size of 3 megawatt and validate it with Petcock and lignite as the main fuel feedstock. The demo unit will be, or is in fact, it has started to be built now in Deyang at the Dongfang boiler test site outside Chengdu city, southwest in China. The project consists of several work packages and it comprises work related to the process design done early in the project. This has been fed further to the feed study, front-end engineering and design. From this, which is also now finalized, this has been fed further to the work package 6, where detailed engineering, the procurement and the construction is ongoing. And next year, the commissioning, startup and operation of the demo unit will go on. But in this webinar, as mentioned, we will focus on the oxygen carrier work being done, that has been done. The oxygen carrier material is in fact a cornerstone of the CLC process. It is normally in the form of metal oxide particles that takes up oxygen from hot air in the air reactor in a highly exothermic reaction, generating heat. The oxygen carrier material transports the oxygen and the heat to the fuel reactor, where they are used to sustain the fuel conversion, which can be slightly endothermic or slightly exothermic, depending on the fuel and oxygen carrier chosen. In this respect, CLC belongs to the oxy-combustion CO2 capture technologies, but the oxygen separation is an inherent part of the process. CLC is most commonly realized using fluidized bed technology. So from this simple reactor principle, we go up to a very simplified scheme of two circulating fluidized bed reactors working together. And higher up in level, a real plant, such as this, which is the 3D model of the Cheers demo unit. The demo unit in Cheers, it has been made flexible, so it holds, in fact, two different configurations, process configurations. A European configuration shown here, where the application case is steam and power generation in refinery. The main feedstock is Petcock, which is very high in fixed carbon, low amount of volatiles. It also contains some sulfur. This design is from Total Energies IFPEN, and you see it, we have a carbon strip at the top of the fuel reactor, and we have L valves to control the oxygen carrier circulation. Biomass is an additional or optional fuel that can be relevant. Then we have the Chinese configuration using the same demo unit with some changes of the process lining, process lines. The application case here is power generation. The main feedstock is lignite, much more volatile content. And this design is from Tsinghua and Dongfang boiler. And you see the carbon strippers is beside the fuel reactor, and the oxygen carrier circulation is controlled by fuel reactor overflow. Okay, so a little bit about the agenda for the rest of the presentations. We started out with a lot of candidates, both acquired natural ores, and some synthetic materials that were manufactured within the project. And the main results of this first screening of these candidates will be presented by Yngve Laring at SINTEF Industry. Some of the candidates were taken further to a second screening in a batch fluidized bed unit, both natural ores and also some of the synthetic materials, the perovskites here. And from this, some were tested also in a 10 kilowatt unit at IFPN. And this will be presented by Kristina Bakuc. Then Inge Sonum from SINTEF will present test work that has been done on a 150 kilowatt unit at SINTEF, where these natural ores, minerals has been tested. Yes, but we have not forgotten the perovskite, the synthetic material either, so it is followed up at the Tsinghua University, and the results from this work will be presented by Lei Liu from Tsinghua. Yes, I think this was in short a first overview here. So then I would like to give the word to Yngve Laring at SINTEF Industry. And
thank you.
Give him the control here.
Yes. Can I have the control here now? Yes, SINTEF's task was the pre-screening of minerals and synthetic material. and look for the lifetime and performance under these conditions given in the shared project. The work I will present here is done mostly by Swan, Martin Sunding, and me. So, there it comes. Okay, sorry, it was a bit late. The outline will be requirement of oxygen carriers, characterization techniques, and material systems screened. What requirement do oxygen carrier material have in the process? And this will always depend on the type of fuel, CLC design, and window of operation. In this case, in shares, we have a higher temperature than regular CLC. It's 950 to 2050. And this is due to there will be slower Petcock gasification and need for higher temperature for having an efficient process. This also always gives a kind of need of a suitable entropy of oxidation for material, meaning that you have active lattice oxygen in the window of operation. And it should also have a reasonable oxygen transfer capacity, circa 3%, for example, because if it's too high, it can also be very detrimental, giving mechanical stress to the oxygen carrier, which will then reduce lifetime. Good kinetics for a specific process based on, in this case, long-term residence time. And OCM stability under redox cycle is also, of course, very important because it's also influencing mechanical strength, the attrition lifetime, which we want to be at least 2,500 hours, ideally, at least. And we need also to take some cost and lifetimes aspects of the materials as well. Often higher cost, higher lifetime, sometimes. Parameter investigated during screening was oxygen transfer capacity by thermogrammetric analysis in the various redox cycles, Q2 stepping for equilibrium oxygen transfer capacities. We also did the reduction kinetics in thermogrammetric analysis and micro-reactor testing. And stability of the OCM, we checked before and after testing by SEM and optical microscopy for characterization of the microstructure to see how it degrades as well, and also with XRD in some cases where this is needed. And also we did some mechanical strength, both by cold attrition and hot attrition. The TGA is a very nice instrument where we can switch between reducing, inert, and oxidizing very fast and in a lot of different cycles. So we can have this automated, and it goes in this case, which you will see later on now, between different hydrogen, high hydrogen concentration and low hydrogen concentration, and also different oxygen concentration, to look at how active it is under a CLC process, which has different conditions on the inlet and outlet. We also did some microanalysis to see, for example, where is the iron magnesium mixed, or is it separate particles and such things as well, to get an overview of how the source is. The minerals, we looked at different material system and minerals. They looked at different analyses and also iron manganese ores. The synthetic part, there is the iron titanium manganese and magnesium silicate and perovskites, which has been tested out. So I think it jumped too fast. Yes. Then when we look at the ilmenite from Titania RC in Telmes, Norway, the first line here, we see that this works very nice from 950 up to 2050. This works under all these conditions and rather good. We see that there's still some activation ongoing here at 950, but this is a good one material which is stabilized after such tests. While with Vietnam and Mozambique, we see that this fails in our test at the higher temperatures, meaning that this is not the very good materials for the system. This will be, because it will have redox, it will also maintain the test better kind of than the ilmenite, but it will not be a suitable candidate. If you look at the rates on this ilmenite compared to other ores we have been testing before, we see that yes, it's a decent capacity, decent kinetics. It's not as high as some of the other ones, but it's something about how if you have particles swelling a lot, then it will also degrade very fast and show very high kinetic, which will fool you because will not be strong and lifetime short. We did some influence with Petcock. We treated in gasification with Petcock first for a while, and then we tested the normal test protocol and compared it with ilmenite, which normal ilmenite, which has not been exposed for Petcock. We see a little bit decrease in capacity, but not kind of any detrimental part, and we couldn't see any detection of other element on the surface after the test either. But I think for this kind of cases, you really need something just operated for a long time in a reactor. They estimated lifetime from hot addition rates in 3 kW rig, get a lifetime around 1,000 hours for 4% hydrogen, and between 4% hydrogen and air. The lifetime will be very depending on the depth of reduction of this material. So it's a little bit hard to really get a good number there, but it might vary, of course, plus minus at least 200-300 hours depending on the operation. The Magnus Iron Ore, we looked at 3 ores from China. The first one here is with high iron content. The 2 first ones with high iron content, and the last one is with high manganese content. The iron content shows very good capacities in one way, but the strength is very low because of iron cations diffuse very fast at high temperatures. It gives swelling and degradation, very fast degradation. While the MN was showing better stability and still a decent capacity in that one. So this was kind of tested further as well. We did a pre-calcination as well to homogenize it because, as you can see here on the some of the fresh samples, the iron and manganese is different places kind of, so we wanted to homogenize a little bit and also react with other species in the sample to get more homogeneous. So even though from this slide it's not too easy to see which one we should select, but based on several criteria, the ilmenite with a good oxygen transfer capacity and the Li with a little bit less oxygen transfer capacity was selected because it's also based on the lifetime of these materials, how it looked like after the initial test. When it comes to synthetic oxygen carrying materials, we have the spinels and the perovskites. The spinels, they show very good and even capacities and very good stability in a way. So this was had a good, but it was a little bit hard to get them very homogeneous in the process we used because we mixed ilmenite and manganese. So if you take that into consideration and the cost of production, ilmenite will be a cheaper source, and this will have a problem to compete with it based on lifetime, which is not extending too much compared to the raw materials. When it comes to the perovskite, we had made 3 different bonds. It's only different composition of the manganese, titanium, and iron composition here, which are affected with a 4-3 bond system here. So the advantage with the perovskite is that they can be tuned to a much higher degree to get higher stability, more or less capacity, and a little bit change in where it released oxygen as well, if it wants CLU or CLC. So and we want something with a high phase stability because then we have a long lifetime, a kind of decent capacity, not too high. We want relatively good reactivity, of course, and a longer lifetime than the other ones. Disadvantage is, of course, cost, especially if it's taken away by ashes as well, but Petcock has low ash content. But it also has some sulfur sensitivity, which can be a disadvantage, but also not necessarily detrimental, depending on the process. The perovskite you show here is the top one, is the most stable one with most titanium dioxide. It has slightly lower capacity than the 2 next one, which has lower titanium content. But this one we didn't see any degradation in the microstructure, while this one shows slightly degradation of the shows some degradation of the microstructure down here. But still very decent to have after such a harsh test like this TGs. So the 8431 was showing really good performance and was taken further in China for upscaling, which will be presented by Lilu afterwards. 611 is the same as been running success with this clue material, showing very good performance for meat and combustion below 950. But we see that this material do not work at 1000 and 1050, meaning that it's very important to design material that fit the purpose and the window of operation for the under CLC conditions. The perovskite type, we have the 8341 and 8431, both react very nicely with the methane, CO, and hydrogen. The methane reaction should, of course, be wished to be slightly better, but sufficient, most likely. And we checked also granulates and versus lab powder, because we make powder in the lab, which is called signed and crushed or such things. But the granulates made by spray granulation. And we saw that we get rather equal performance on the material, and which is comparable, which is very nice. This also is small scale or kilo batches. When it comes to effect of H2S, we see that when we run CLC, it do not affect the material so much, with the sulfur part really in the middle there, and back to normal condition without sulfur. We say 200 ppm sulfur. When it comes to if we take out the clue effect down to argon or inert atmosphere, we see that we get a concentration in sulfur, most likely on the surfaces in this case. But after some CLC deeper redox, it gets back to normal again, meaning that the sulfur is can be taken off, and it's not so critical, especially for this compound here. For the CMTF 8431, it seems to be a little bit more critical. This one also has a little bit more change in microstructure, giving high surface areas and more than sulfur absorption. But you see, this one also can be regained after with some deeper redox, which is also in the case of the Shares project, where we do deeper redox rather than in the normal CLC type system we use at other places. We did some co-attrition of this material as well, and we see that they are equal to other good materials like nickel, nickel and copper. A little bit not fully so good as the nickel alumnite, but they are in this same range as a lot of other material tested before, meaning that they have a good strength. The one which has the last strength is the one with a little bit too low sinteric temperature, making it a little bit more less strong. So this is important to optimize. And a summary of the screening of toxin carrying materials is that the inlet from Norway is as good reactivity. The strength lifetime is a little bit moderate, around 1000 hours. We should wish a little bit more. The cost is low, and the source utilization is depending on how we look at it. We got fraction from TLS, which we can use nearly all of. At least 85% in some of the cases. But if you look at the total sieving of a whole system, you only utilize a small fraction of mineral from an ore, for example. Especially from the Magnus ore, Li ore from China, you will always have a lot more dust in the Magnus ore because it's easier to crush, meaning that you get lower fraction, which you can use for a CLC system in the long run. If you compare this with synthetic materials, where you can produce the correct fraction directly, meaning that the less time, less losses here. The Li ore is also good, moderate low strength, medium cost, and also synthetic here, high reactivity, high strength, but it's also high cost, which is or higher cost at least than the other one. And this one, last one as well, the synthetic one, because you need a fabrication part. But we should not forget that those ones need pre-sintering sometimes, crushing and sieving, which also make them not as cheap as one thinks often. But the ilmenite we buy with low cost are already sealed and crushed, which is a very benefit for us. So therefore, the ilmenite was the one which was selected for the first generation, and yeah, this we can come back to also in the next presentation as well, where I did this even more deeper selection of the materials. Thank you.
Thank you very much, Yngve. That was very good. So then if there are any questions or comments, please use the Q&A possibility as mentioned by Todd. Now I will give the word further to Christina, who will
Yes, thank you,
present from
Øyvind.
IFPEN.
Good morning, everyone. Bonjour de France. In this section of the webinar, I would like to present to you the results of multi-scale screening of oxygen carriers that has been performed here in IFPEN for the selection of the best candidate for the oxygen carrier to be used in the demonstration units of 3 MW, that is to see its startup and its first operation, hopefully during this year. As you have seen in Yngve's presentation, the oxygen carrier development has seen a significant growth and significant levels of batch screening. And after this first level of screening, 3 different materials or group of materials were sent to IFPEN for further testing. Namely, those were the ilmenite ores from different origins, perovskites as the only synthetic materials, and iron manganese ores locally mined in China, which gives them a certain benefit for material availability. In order to select the best performing oxygen carrier throughout this screening process, we would follow some of the key parameters, starting with the morphological changes of material that were systematically followed before and after each activation phase to see if there were any significant losses in the activity of material or in its general porosity. Further, we looked for good resistance to the temperature of operation, which is quite high, as you have seen in the previous process presentations, and good performance in the oxygen transfer. So here we follow some of the values such as the R0 delta X, which is namely the mass of oxygen transferred to the fuel from the oxygen carrying material. And of course, the fuel conversion, which can vary depending on the source chosen. And fuel conversion for gaseous fuel and solid fuel is not necessarily always the same in the level of the performance. Of course, what allows us the second level of screening, that is the pilot testing, is to actually assess the mechanical attrition of the material, which can be very important for the following injections of the material and the overall lifetime. And of course, it affects the OPEX of the process. Finally, we also considered throughout these tests the overall availability of the material. If it has to be produced, such as the synthetic ore, what is the overall production cost? Or if it is a naturally occurring mineral, what is the overall pre-treatment cost to actually put it online? The first level of screening was performed in the batch unit, which is the fluidized bed unit that you see here on the right. Oxygen carrier material would be placed on a plate, and then fluidizing bed condition would be achieved by injecting a certain mixture of inlet gases. 2 types of tests were performed, namely, first being the aging test to see what was the lifetime of the material in exposure to very reducing atmosphere of methane and over a high number of cycles, around 250 redox cycles would be performed. A second type of testing would be with the actual solid fuel injection, where Petcock would be injected to the fluidized bed from the top, as you can see in the scheme on the right. And again, the outlet gases would be analyzed with the same infrared analyzer, and the outlet flow rates would be measured as well. In this case, we wanted to check for the performance of the oxygen carrier with the actual solid fuel, where there is an additional step of Petcock gasification, and that can significantly influence the kinetics of the overall system. Here, I give you the first results regarding the ilmenite ores. So following the batch screening, we found that ilmenite ores require certain activation period, but after being activated, they achieve quite high values of conversion of methane, as well as this R0 delta X value, which means that the oxygen transfer capacity is quite high for ilmenite ores. As for the kinetic screening tests with Petcock injection, we found that they give satisfying reactivity, and in the conditions of higher water content or higher temperature content, they would have better Petcock gasifications. Out of the all ilmenite ores tested, titanium mine ores performed the best. However, we still had to make the choice between the ilmenite T1 or T2 material. They are quite similar. They come from the same mine, so composition is almost the same. However, ilmenite T1 has higher water contents, which leads to the fact that ilmenite T2 shows higher agglomeration affinities. And this could be problematic in the condition of continuous circulation. So we decided to perform additional aging tests where to the inlet fluidization gases, actually different water contents would be added. In this case, we desired to compare once again the performance of ilmenite T2 and ilmenite T1. What we found was that upon addition of water, there were no longer agglomeration issues with ilmenite T2. And since overall pre-sieving and pre-treatment is significantly cheaper for ilmenite T2, we would say that overall reactivity is high enough that we can suggest ilmenite T2 for further tests. Following with the results of perovskites, they are the only synthetic materials. And as you can see here, they have no activation periods that were noticed during the aging tests. However, for the similar gas flow rates, somewhat lower methane conversion was observed than with previously seen ilmenites. Also, we have found a certain decrease in activation for repeated cycles, for repeated redox cycles. And for this reason, we decided to perform additional kinetic screenings. What this has shown us is that upon multiple Petcock injections, there is certain sulfur adsorption on the surface of these materials. Since perovskites have low porosity, this leads to lower interactions on the surface of the material and overall lower activity. So in the case of Petcock study, they would not be the best candidate for further tests. However, with a different fuel, given the high values of oxygen transfer capacity, they could still be a very good candidate. Following with the results of LYMN ores from China, we see similar trends of activation as we have seen previously with ilmenite. However, the values for methane conversion are somewhat lower. Still, overall reactivity of the material is quite satisfying, with one important addition that during the characterization of the material after the activation tests, we have noticed a certain increase in particle porosity, which could indicate higher affinity for attrition. And this is important for particle lifetime overall. So following the tests in fluidized batch reactors and the first screening, we have decided to perform additional tests in 10 kilowatt pilot unit, which allows for continuous operation. As a representative of ilmenite ores, we chose titanium T1, since, as I have said, they have very similar performance between T1 and T2. And from iron manganese ores, we would test the LYMN, since the goal of this level of screening was to find the best possible candidate for the Petcock study. And of course, propose it for the operation in the 3 megawatt demonstration unit. So this is the presentation of the 10 kilowatt pilot unit that has been used for continuous operation tests. Here in this little scheme, you see the fuel reactor and only one of the air reactors. However, in reality, we have 2 air reactors to achieve the complete oxidation of the material. Furthermore, there is a carbon stripper above the fuel reactor that serves for separating the unreacted Petcock in the case of Petcock injection, and the entire system is fully optimized, where the most significant operating conditions that were followed throughout this test are, of course, the temperature of the fuel reactor, the flow rate of the inlet gases that could be adjusted, the methane concentration to adjust the level of reduction, and in the case of gas fuel tests, and of course, the flow rate of oxygen carrier itself, which has to be ensured to be continuous. What is important for this unit is that it allows us for closer representation of the lifetime of the oxygen carrier at the actual unit, and it can show us the agglomeration potential of different oxygen carriers itself. Of course, throughout the entire test in the pilot unit, we would closely follow the key reactivity indicators, which are once again the values of R0 delta X, or oxygen transfer capacity, different fuel conversions that are targeted to be as high as possible, and also the ratio of CO to CO2 at the outlet of fuel reactor, which we aim to be as low as possible to indicate good gasification of the Petcock. What we have found following the gas fuel performance tests in the reduction atmosphere of methane is that ilmenite ores achieve high conversions of methane, as you can see in the red points here on the right, while the conversion with LYMN is lower in the case of methane or gas fuel conversion. And this would indicate that LYMN is more sensitive to high reduction atmosphere than is ilmenite. However, in the performance with solid test, LYMN would achieve significantly higher conversions. So this is the performance in the highest possible reduction atmosphere that we see here. For the values of oxygen transfer capacities, or R0 delta X, in both cases, we see that we reach satisfying values. However, the time to reach it is not the same. So ilmenite requires higher activation period than is the case for LYMN, because they already start with significantly higher values for R0 delta X of 0.7 with respect to approximately 0.4 in the case of ilmenite. Finally, if we take a look at the values of the concentration or the ratios of CO to CO2 at fuel reactor outlet, more performing material seems to be ilmenite, as it is way lower in the values than in the case of LYMN ore. Finally, if we look more closely at the morphological changes of the material during these tests with gas fuel in a very highly reducing atmosphere, we can see certain phase changes in both cases. So both ilmenite and LYMN have a tendency to agglomerate, which would indicate that this could not be avoided in a large-scale operation, but the formations are different. So in case of ilmenite, we can see a form of hematite layer on the surface, and in the case of LYMN, certain oxide islands are noticeable on the surface of the material. And if we take a look at the attrition capabilities, ilmenite would see some loss of the particles that could be collected at the outlet of carbon stripper. So very fine particles, less than 100 micrometers, would be collected only after the fuel injection in the case of ilmenite, while for LYMN, they would be noticeable already in cold flow, so when only fluidization is achieved. This also leads, it seems, to a longer lifetime in circulation for the ilmenite, which under the gas fuel was around 770 hours. And I would have to specify here that the lifetime of the fuel on Petcock injection, so under solid fuel, is about twice as high because we have a much lower reduction atmosphere. So based on this gas fuel performance test, ilmenite seems to behave better. However, additional solid fuel performance tests were performed, and the reason for this was twofold. On the one hand, we wanted to also test for the values of Petcock conversion and oxygen transfer capacities, but also we wanted to find the best indicators for the operation, which would help for operating the actual demonstration unit at the large scale. So what we found was that the fuel reactor temperature has, of course, positive effect on oxygen transfer capacities, which is more pronounced in the case of LYMN than it is for ilmenite. In any case, the trend is the same for both of these materials for the same parameter. In the case of the steam content in the fluidization gases, steam content seems to have a much more pronounced effect when we operate with ilmenite, while during the operation with LYMN, the effect of the steam content to the overall values of oxygen transfer capacity seem to be quite negligible. As for the Petcock flow rate, as it would be expected, if we provide more fuel, there is more exchange of oxygen. So we achieve higher values of R0 delta X in both cases. However, for the oxygen carrier flow rate, we find that if we push for higher values of oxygen carrier flow rates during the operation, this will actually reduce the capacity for oxygen transfer. And it makes sense since it would probably allow for lower contacting between the oxygen carrier and the actual fuel. So this is something that should be avoided normally during the operation. So if we take into account all the most important parameters that we identified for the operation at different scales, but more importantly, that would be exploitable for the demonstration unit, we find that for the gas fuel conversion, ilmenite definitely shows better characteristics, while for solid fuel conversions, LYMN has achieved higher values of fuel conversion. Nevertheless, the CO to CO2 ratio was much closer to 0 in operation with ilmenite, which is a more satisfying result that we look for. The attrition affinity was definitely lower in the case of ilmenite, so we would say that the performance is better for ilmenite in this parameter as well. And finally, if we look at the production costs and the overall pre-treatment costs, I would say for these two ores, ilmenite has lower overall pre-treatment costs than LYMN. So based on all of these parameters taken together, we would propose that ilmenite should be used as the material of choice. And in connection with the batch screening results, ilmenite T2 would probably be the best candidate based on the screening that was performed in IFPN. So thank you very much. This is the end of our part.
Thank you very much, Christina, for that. It's very good, interesting. Yes, still you can just use the Q&A and we will come back to you there. We progress further. So so then I will give the word to Inge Sonnum at SINTEF Energy Research, who will talk about some tests done at SINTEF on the 150 kilowatt pilot unit. So
thank
please,
you.
Inge.
Thank you, Øyvind. Yeah, this work was performed by Øyvind and Roger Khalil and myself. Let's see there. So this is the reactor system. It's two interconnected fluidized beds. But the special thing about this reactor is maybe the lifter. So the particle transport can either be the normal way up the fuel reactor through the cyclone and to the air reactor, and it will be both that way and down to this lifter. where it is fluidized, and so we can kind of control by the fluidization how much is going in that way. Yeah, the fuel reactor is quite small, designed for quite high velocity and high particle transport. So the residence time is quite low in the fuel reactor. Sorry. And we don't have a carbon stripper to the system. So that means that this system works best for reactive fuels, because the gasification is quite low residence time for the gasification to take place. Yes, we also run this in autothermal operation, so we cannot really set the temperature. You have to use a process to adjust to the right temperature. The only heating we have is the electric heater to the primary air to the air reactor. Yeah, here we see some pictures of the reactor installed in this tent hall. We have, this is before it was insulated from the top and after insulation. Yeah, we tested the 3 oxygen carriers, two ilmenites, the T1 and T2, which should be very similar in composition. The only thing is the size. And this T1 is what we have used the most. And we tested this Magnus ore, which also contained quite a lot of dust, which made some operational problems for us. And the fuels tested, we tested Petcock with 2 different particle size fractions, and this wood pellets from Arba flame, which is brown because of a steam treatment in the production process. And we tested 3 sizes of this, of the whole pellets, crushed and sieved, and crushed and unsieved, so with the smaller small particles. So some results. The 2 main parameters to evaluate the CLC process, I would say, is the CO2 capture efficiency and the fuel reactor gas conversion efficiency. To the left, we see, this is the result for the ilmenite T1. This is the 3 sizes of biomass. And we are around 90% on the capture efficiency. And here is 25% Petcock mixed with the biomass, 50% Petcock and 100% Petcock. And then we see a really drastic drop in the CO2 capture efficiency, which is because quite a lot of the fuel is not gasified in the fuel reactor and is transferred to the air reactor, where it combusts and leaves the air reactor as CO2. Yeah, and the fuel reactor gas conversion efficiency is convenient because it's only dependent on the gas composition. We can calculate from the gas composition out of the fuel reactor. It's defined through this oxygen demand, which is the ratio between the oxygen needed to convert the unconverted gases to the stoichiometric oxygen. And the gas conversion efficiency is then 100% minus the oxygen demand in percent. So the same experiments then show that for biomass, we are around 80% fuel reactor gas conversion efficiency. And it actually increases the more the petcoke we put in, which may seem strange, but it's because less gas is really produced. So a lot of the fuel goes to the air reactor. And then it's an easier task to convert the gas, the little gas that is produced, to CO2 and water vapor. Yeah, here we see the same figures. Only here are the 3 oxygen carriers included, and for biomass and petcoke. Yeah, the carbon capture efficiency was high for all oxygen carriers when using biomass as fuel. When using ilmenite, it was low, but it seemed like the manganese ore was a bit better. Yeah, the gas conversion efficiency, we saw that the manganese ore did not perform as well as the ilmenites, both for biomass and for the petcoke. More pronounced with the biomass. And then if we look at the 2 comparable experiments with the ilmenite and manganese ore with the wood as fuel, and we see the gas composition out of the fuel reactor. If we, for instance, look at the yellow curve, which is the CO, with the ilmenite we were 6.5% CO, but with the manganese ore at quite similar conditions, we were up to almost 17%. And we also see it on the methane and the hydrogen. And this is actually in line with what the IFP found, that the gas conversion was not as good with the manganese ore. Yeah, we also did stress testing to see if there were problems with agglomerations with the ilmenite T1 particles. So we did this by heating up the reactor and also running in CLC mode at high temperature then we used hydrogen and propane as fuel. And we tried to run it so the particles would be as reduced as possible, as that is when it's the most danger for agglomeration. And then we suddenly stopped the fluidization by pushing the emergency shutdown button, and we let the reactors or the particle beds just lie still for up to 50 minutes. And then we tried to fluidize it again to see if it was only 2 big lumps or one in each reactor, but we managed to fluidize it every time. So but when we emptied the reactor after the test, we found some agglomerates, but it was not very strong. It could easily be crushed with the fingers. And we sent some of these agglomerates for analysis in Oslo. And if you see on these EDS pictures, we see that the iron is the red stuff on the surface here is iron. So this is known that the iron tends to migrate to the surface of these ilmenite particles. And it seems like this is the thing that causes the particles to stick together. Okay, so to sum up, high capture efficiency, above 90%, were achieved for all three oxygen carriers when using wood as fuel, but poor capture efficiency, 30 to 50 when using for all the three candidates when using Petcock as fuel, but that is because our reactor design to low residence time and not a carbon stripper. Yeah, the fuel reactor gas conversion efficiency with around 80% for ilmenite, but below 70% for the manganese ore with wood as fuel. Yeah, and ilmenite does not seem to have a high propensity to agglomerate, at least not in our rig, although some agglomeration was observed after stress testing. So out of the three oxygen carriers tested, the ilmenites performed better, and the ilmenite T2 matches the particle size of the demo unit and is therefore the preferred candidate. Thank you.
Thank you very much, Inge, for that. That's good. Then we just progress further to the presentation from Tsinghua, and I will give the control here now to Lei Liu, who will present on this perovskite material. So please, Lei Liu.
Okay. Thanks a lot to Owen. Okay, I try my control. Sorry, I can't control my screen. Okay. Good morning, Europe, and good afternoon, China. I'm Lei Liu from Tsinghua University. I will share some studies on oxygen carrier in Tsinghua, and this work is collaborated with Ingve and Joy in SINTEF. In the CHAIRS project, we focus on the studying CMTF as oxygen carrier, meaning from the 4 sections, including a long-term oxidization and reduction cycles in Mfbta and the reaction kinetics of CMTF and the sulfur effects on CMTF. Finally, we realized the industrial scale production of CMTF. For a large-scale CLC plant, oxygen carrier must possess some chemical and physical properties. For example, the oxidization kinetics determines the solid inventory, pressure drop, and final optional consumption in the air reactor. If oxygen carrier can release 1.2 to 1.3 oxygen in the fuel reactor, that is some clue property. The released oxygen can reduce the ambient gas in the fuel reactor overnight. Also, oxygen carrier will not agglomerate even if deeply reduced at a high temperature in the fuel reactor. Also, the oxygen carrier must be low price and no toxic. There is no expensive and toxic elements in the material. Based on above performance, SINTEF developed some CMTF oxygen carrier and sent 2 of them to Tsinghua University for research. This material consists of calcium, manganese, Ti, and iron. you can see all the elements and the raw material are very cheap and low toxic. After calcination at 1350 degree, perovskite structure formed in the material, and the two oxygen carrier has similar perovskite structure. So this the particle size, true density, and the BET surface area is listed in this table. Then we use the microfluidics by the thermogravitometric analysis (Mfbta) to study the multiple cycle and the kinetics of CMTF. The code of Mfbta is the bubbling by the reaction. We add 350 microgram CMTF particles into the reactor for the redox kinetics test, and 3 gram particles for the oxygen release test, and the other bond materials is silica sand. During the reduction, CMTF will lose the oxygen and its mass will decrease. Where in the oxidization, CMTF can get the oxygen and the mass increase. So the principle of Mfbta is measure the real-time mass change during the gas-solid reaction. Use a high-precision mass transfer to obtain the reactivity and kinetics at fluidized states. And then we obtain its reactivity at different temperatures and different gas. Firstly, we carry out a long-term redox stability experiment for CMTF. Totally 1,000 cycles were conducted. CMTF has no decay in reactivity and low agglomeration during the whole test. Even if we stop the gas supply, there is no agglomeration. Then CMTF has a very fast oxidation rate. Just need 4 seconds to finish the oxidation. That means there needed a residence time and bond inventory in the air reactor is very low. So the pressure drop in the air reactor is also very low. You can see CMTF also can be reduced fastly by hydrogen. Just need 30 seconds to full reduction. We also find the CMTF can release 1.3% oxygen in the air reactor just within 20 seconds. So this oxygen can enhance the gas conversion in the fuel reactor. Then we studied the sulfur effects on the CMTF kinetics at 900 degrees. Sulfur almost has no influence on the reduction rate. There is a benefit. The benefit is sulfur can increase the oxygen transfer capacity. Also, because of sulfur, the oxidation kinetics decay 1/2, but the reaction rate is still very fast enough. Just spend 8 seconds to regenerate 4% oxygen. From the SEM images, sulfur can react with the CMTF to form sulfate, cover the particle surface, and further to affect its reactivity. In order to upscale the CMTF production, we explored a spray drilling process to produce the CMTF at industrial scale by using these conventional raw materials with high purity and moderate price to make a slurry in a mixer. And then we using a spray drilling device to draw the droplets and forming the CMTF particles in the bottom. Most of the connected particles is in the range of 35 to 500 micrometer. In the first stage, we totally produced 1,000 kilogram particles. The total price, including purchase raw materials, granulation, and calcination, is close to $2,000 per ton. Then we study the industrial scale CMTF's kinetics and compare to the level scale CMTF. We find the industrial scale CMTF has a very similar oxygen release rate, oxidization rate, and reduction rate to the level scale CMTF. Also, the attrition rate and the XRD results are very similar. So the uplink production of CMTF is very successful. Based on the reaction kinetics, we can evaluate the required bond inventory in air reactor and field reactor. These equations, the reaction rate is from the Mfbta results. Then, according to the bond inventory, we can calculate the bed pressure drop. As we know, the fan need to overcome the pressure drop in the field reactor and the air reactor. So we can calculate the fan power by the equations. We can see the results. The totally needed bond inventory is 78 kilogram per megawatt. The bond inventory, it should be true. The bond inventory is to know just because we calculate the FR bond inventory by the hydrogen conversion, not according to the coal or char gasification. But at the same conditions, the bond inventory is far lower than that of other oxygen carriers, ilmenite, manganese, and copper. Yeah. Also, the fan power is 7 to 7.6 lower than that of other oxygen carrier. In summary, CMTF is a very good oxygen carrier without any agglomeration during 1,000 redox cycles. CMTF can be fully oxidized within just 4 seconds, meaning a very low pressure drop in air. CMTF also has a faster reduction kinetics. CMTF can release about 0.3% oxygen in the air reactor with just 20 seconds for unburned gas conversion. Sulfur can enhance the oxygen transport capacity and has almost no effect on the kinetics at 900 degrees. Upscaling preparation of the perovskite particles at an industrial scale was realized. And the last conclusion is CMTF has great potential to decrease the operational cost due to the lowest fine energy consumption. Okay, thank you very much.
Thank you very much for that, Lei. Yes, it's really nice to see the results from this CMTF perovskite studies you have done here. Yes, we have 5 minutes left now, so I will just make a short summary of what we have seen. So we have investigated some natural ores, and we have found rather similar performance between ilmenites and manganese ore. Maybe a little bit less gas conversion on the manganese ore, or not maybe, it is. And it also has some higher attrition rate and fines production. And since the polarize of the ilmenite is rather good compared to the manganese ore for the pre-processing, it seems to be the best candidate to use the ilmenite. And we had 2 alternatives, and the one T2, which has the more favorable particle size, is the one that is chosen here. Some early problems with agglomeration was solved and could be explained, and we feel more confident that this would work than in the demo unit. And the agglomeration issues is, of course, not disappeared to 100%. This is still a concern for the demo unit. So careful fluidization of the systems, especially low velocity and dense zones like L valves and steam addition, we believe this can be manageable. However, we have also seen that the synthetic material, the CMTF perovskite, is a really good candidate and can be an alternative for fuels with low sulfur content. At least we saw in the Petcock tests that it was deactivated by the sulfur content in this Petcock. Yes, so yeah, this is the summary repeated in a graphical way, nothing more. Yes, so I think that this would end our presentation here. So I would thank everyone listening and following this for your attention, and I hope we can have some discussion and questions. If we cannot take it now, you have our emails here. We can communicate that, or in the Q&A. So, Todd, do you have any comments? Do you see any?
That was excellent, fantastic presentations, and you finished in time. That's really well done. So we have recorded today's webinar, and it will be published on the Cheers CLC YouTube channel. And I will make a notice of that on our webpage and on LinkedIn later today. So you can pass that on to your colleagues who are also interested.
Okay, so if there are nothing else that should be answered or commented now, or if you can take that presenter by presenter, if there has been something,
so
we could probably end then.
I suggest you take a screenshot of the contact details, and if you have further questions, please reach out to our researchers. They would be very happy to discuss things in more detail with you. But I think that concludes our webinar.
Okay.
Thank you very much. Thank you, everyone.
Thank you very much.
Thank you
Thank
very
you.
much.
Thank you.